Okay, so yeah, so today's session we're going to talk about the high-level design architecture of the zkEVM, like different modules, functions, and then maybe like different circuits, like from both our team like Scroll and also as well as like in the Polygon Hermits, like how do we like design our zkEVMs? So we can go like a bit longer time for today's session so that we can cover like a little bit more details into that. But I was expect like still maybe like still a very high level architecture designs for the zkEVMs. And also, by the way, I also uploaded the recordings for the day 1, day 2 here. So you should have access to this Notion page, which like it's the link is provided in the calendar invite. So you will be able to open this link and then check out the schedules and as well as the recordings. And we're also collecting the slides very soon to share it here. So you can have like some early access to if you want to review anything that you want to go over in the previous sessions. Okay, so with that, probably we can get started. So today I'm going to present the Scroll zkEVM designs first, and then after that, Carlos and Jordi will talk about like Hermit zkEVM design and some code examples. Okay, so yeah, hello everyone, welcome to today's sessions. And so today I'm going to talk about Scroll zkEVM designs. So before that, I think the first things I want to cover in the topic is what does the zkEVM need to prove? So for those like who maybe not very familiar with the EVM, Ethereum, and how EVM works, so initially like at every timestamp t, so you will have a word state with like a Merkle partition tree, and then have like a root of the state, which is like it's the current snapshot of the word state. And then at this time, like you will receive a new transaction trying to either do some transfers from one account to another account or call a smart contract to execute some bytecode. So what you're going to do is you're going to pass the word state, the current word state, and then the transaction into the Ethereum virtual machine. So this is the runtime or the executor for the Ethereum. So I'm going to process the transactions given the current word state. And then the output is that it will end up with a new word state at a t+1 with a new state root here. So there's like a root prime. So if you look more into details like how EVM works internally, so inside the EVM, this is a virtual machine. So you have an executor that's going to execute every opcode as a stack and memory. That's all like those are transient storage that you're going to push and pop like from the stack and then load and save certain like things into the memory, which were going to disappear after each executions. And also you can access two external persistent storage. One is the bytecode database. So you're going to know like which contract you're going to execute by loading the bytecode, the contract bytecode from the storage. And another is the storage which corresponding to this state tree here. So every time, like if you want to write anything persistent, it will also reflect some changes into this Merkle trees, and then we'll go modify some paths and adding some more nodes here, so on, and then so on and so forth. So if you look into like more into details, like during the execution, what we're going to happen is that you'll go iterate over through this bytecode defined inside the smart contract. You'll first like at a step like every step, you're going to execute some bytecode. And then if you maybe like go into some loop inside your bytecode, or you maybe also call some other you maybe call some other smart contract inside that. So it end up like it's like after you execute the EVM given the transaction and the state root, you will result in a unique like the execution trace here, which like step by step iterate like each transaction, each opcode defined in the smart contract. So what the zkEVM is trying to do is taking the spec of the Ethereum virtual machine, like for defined in the yellow paper of the Ethereum, and then you're going to output like you're taking like all of specs of each opcode, how you're going to process certain things, how you're going to like model the stack and memories, and then how to like load certain informations from the public input, from the transaction call data and from the storage. So you're taking that spec, and then that ends up with the zkEVM. And then when you're trying to invoke the zkEVM to generate certain proof, what you're going to prove is that you will use the current world state root as the input data, and then the transaction as like another part of the input data, and passing to the zkEVM. They're going to instantiate a zkEVM proof instance. And what you're trying to prove for the zkEVM is trying to prove this execution trace is correct, and it's also it's unique here. Thus, it means like given this current world state and then the current transaction, like the transaction you're going to input to the zkEVM, this is the only and the valid execution trace you can execute by using the zkEVM spec. So to be more specific, so what does the zkEVM want to prove exactly? So first, they want to prove that this execution trace is correct and unique. And then the second is that the global state can transit from the old root to the new root. So these are the two things, like the most important things that zkEVM trying to prove. So how should we prove this correctness of these two things? So I listed here 4 things I think that would be important that you need to cover inside the zkEVM. The first is that the program executes the correct contract bytecode. That means like you're not executing an arbitrary code. You're like adding into the trace into the witness. So executing like the correct contract bytecode from the bytecode database, the contract database. And then second, the program can load the correct input data, like including the transaction code data, state root, and then some block information like into the block header informations. And then the third is that the execution of each opcode is the same, behaves as exactly the same as what EVM spec wrote here. So it means like so all of the computation, like the arithmetic computation of each opcode is executed correctly inside your circuit, and that could be only the case like you can in the circuit using constrain. And also that also imply that the stack and the memory operations, like those are modeled correctly. And then those corner cases in the opcodes, for example, like different gas computation, like some hot and then and cold storage you're going to load, that's all considered inside the circuit. And then third things like different error cases need to be handled correctly. For example, sometimes if you run like into just like the EVM run into certain error cases, it's also a valid trace from like execution perspective. So that means like you also need to handle those error cases correctly inside the circuit. So for example, like you went into like insufficient balance, you went into like the out of gas error. So those kind of error also need to be have like a corresponding state inside the zkEVM. And the fourth is that the storage reads and write will update the root correctly. So that means that you can prove the state root transits from the old root and then to the new root by applying all of the storage reads and writes, and then you can update it correctly. Okay, so next, like I'm going to go through that is first I'll talk about how we constrain the execution trace by starting from the scratch. That can be easier, like we could go like a little bit from like easier cases and then to like more advanced into more complicated cases. So we see like how we can going to do that. So initially, as we showed before, after you execute some transaction with the current state root, you end up with an execution trace. So then you can expand those execution trace and then feeding into a circuit, like we call it EVM circuit, which is the main processors that are going to process and approve that state, like each opcode is inside the execution trace is executed correctly inside the EVM circuit. So remember, like in the Halo 2, or like actually in the Pew, it's also similar. You have a 2-dimensional matrix. They have like different rows and different columns. So here the columns can be prefixed, and then but the rows is like you can allocate different rows for each step. So you can think like we can allocate a slot inside the EVM circuit for each step you execute inside the execution trace. So the difference is probably, I guess, that inside the Halo 2, we allow each step can contain multiple rows. That each step like can access, like use the cells inside those multiple rows to constitute to roll these constraints and then put into the witness into this your step slot. And here the number of rows inside each step can vary, like depending on the actual opcodes executed. So for example, in the push opcode, it could be slightly easier to verify so that you have fewer rows you need to allocate it for this slot. And then if you have like the example for more complicated like add or multiply, those more complicated opcodes can end up with more rows inside a step, inside each step slot. So this can be depending on like how many constraints and how many witness data you need to put into each associated with each opcode. By the way, if you have any questions, like feel free to ask me, interrupt me. Just unmute yourself, or you can also put into a chat so that I can also address any questions you have. Okay, so if you look into more details, like into each slot, what constitutes it has three sections inside each step slot. So so first, like the slot is that the first section is the step context, which you think of like it's a context register. It's going to keep certain like informations that, for example, like stack pointers, like program counter, those kind of information is to keep inside your step context, so that you can know like what opcodes you're going to execute and what step we are at. And then second is the case switch. So here the case switch is like an array of selectors, but here the selector is more like the advanced selector, so that it's not a fixed selector. If you think of like in the Halo 2 columns, the selector usually to be a fixed column. But here the case switch is like they are all configurable selectors, and then each selector can be only like each cell inside of this case switch can be only 1 or 0. So that once like you turn on certain selectors, it will assume like the third section, like opcode specific witness, were put into certain values into the certain in a certain layout, and then you also trigger like the turn on those constraints to constrain this opcode specific constraints as well. So that's why like the third section will be opcode specific witness. Okay, so let's look at like what we put into the step context registers. So these are like all the fields we put inside the step context. So first we have RW counter. So this is a global counter that we're going to use to count for how many stack, memory, and storage operations have did inside these transactions, or if you have multiple transactions, like it will be shared uniquely growing across all of the transactions. So this is like a unique counter for like all of the state operations you did, like any reads or writes to the stack, memory, and the storage will be increase this RW counter for one. And then second, this is call ID, which is also a unique ID to identify the current call. So the reason we need to have this call ID is because inside one transaction, like when you execute one smart contract, it can be potentially you can call other smart contract. So you inside one transaction, you potentially can still have multiple call ID. So this call ID can help us to distinguish the stack and memory across multiple different calls inside inside one transaction executing trace. And the third is the code hash. So basically, that's the current executed executing bytecode the code hash of the current executed smart contract. And then the fourth is the program counter, the PC, and then the stack pointer, which like means like how many items like you have inside the stack. And then the gas left is basically the gas that's going to left inside your transactions. If like you went like go below 0, like or like if you don't have enough gas to execute the next opcode, then we'll end up within the out of gas arrow here. And then the next one is the memory word size. So it means like we need to count the current memory size and then that's like the memory size is counted in terms of the number of EVM words. So it's in 250 bits, 256 bits. And so this can be used to help to calculate the gas cost for when you expand the memory to a larger size. And then the last one is the reversible write counter. So this is actually a snapshot for with the RW counter. That's going to use to revert the writes to the storage. So it means like when you're trying to when you call into another smart contract and it failed internally, then you need to revert the writes into inside like anything like it did within that range, then you use this reversible write counter to revert the changes you write to the storage. Any question to this? Okay, I'll go. And then the second section is the case switch, as I explained a little bit before. So it constitutes like a binary, a bunch of binary selectors corresponding to all of the EVM opcodes and the error cases you have. And then you need to constrain that exactly only one selector is turned on, switched on. That means like you cannot execute like constrain multiple opcodes, like or multiple errors within each step. So in order to like, if you put into the constraint to that, it's quite simple. So first, like you add a constraint for every selectors here to be like only 1 or 0, and then you say like all of them adds up to 1. So like only one is turned on. And then we actually did some optimizations by actually it's like fewer states than the number of opcodes you exist inside the Ethereum virtual machines. Because we found like the certain opcodes, they have very similar behavior, so that you can use one single logic inside the circuit to constrain different opcodes. So here I list like a few examples. There could be like a little bit more inside the actual circuits. So for example, you can think the add and sub, you can combine them into one single execution state. So on the left side, so here is the opcodes, and then the right side is the corresponding execution state name. So that, for example, like add and sub, you can just swap the operands sequence so that you can then turn into a subtract into an addition. And then the multiply, division, and the mod, so they can be like a constituted with a simple, same part of logic inside the constraints inside the step. So you just only need to differentiate, like if you can use like a simple gadget called like A times B plus C equals to D, that's going to constitute for all of the cases for multiply, division, and the mod. And then similarly for the shift left and shift right, you can also combine into one single state. And then the sign division and the sign mod, you can also combine them into one single execution state. So, and then there's some other example, like the comparison, you can like all compare, put into like one simple execution state and a slot. And then like there's certain like memory operations, you can combine them into like a single execution state. And so you could have like a simple so each execution state will correspond to a simple like a gadget that's going to constrain them altogether. Okay, so the last things that I'm going to talk about is the opcode specific constraints. So witness the last sections. So here inside these sections, you're going to have like so those witnesses are very specific to each opcode. Are going to use to prove the correctness of this specific opcode. So here, for example, for this add opcode examples, so we can break down an EVM word like into high and low, which each one with a 128 bit. So you can represent a EVM word into a high 128 bit and a low 128 bit. And then you basically want to prove like A plus B equal to C. So, and then you add like 2 more cells to record the carries that are going to overflow by adding the low part and adding the high part. So you have like 2 auxiliary cells you allocated specific to this add opcode. So the constraint is also fairly simple. So you're seeing like when SAD is turned on. So here, like you see like this, there's a selector will be multiply all of the constraints that are associated with this add opcode. So you see like A low plus B low minus C low and minus carry 0 times the 2 to 128 will be equal to 0. And then A high plus B high plus carry 0, which like carry over from the low part, and then minus C high minus carry 1 times 2 to the 128 equal to 0. So basically you have 2 constraints here that is only specific to this add opcode. I'm going to constrain the calculation of this add opcode is done correctly. So this is like all you need to constrain that. And then for other opcodes, for example, let's say if we're going to do the multiply, maybe you need more cells you need more auxiliary cells to help you to prove like A multiply B equal to C, like when you mod like 2 to the 256. So you have like the additional like cells, but that will be going to only, and also you have like other constraints, but that will be all multiplied by this small selectors. That's going to constrain like for the multiplications, for the multiplication related constraints. Okay, so this is like the a few things like you need to do like inside the step. So what else you need to constrain inside the step? Because for the previous part, like those constraints are not enough to constrain all the behavior inside the step. So the first step is going to constrain that you need to constrain the context transition from the current step to the next step. So what does that mean? That, for example, you need to constrain the program counter will increase correctly, the step pointer will behave same things correctly, and then the gas left. So you need to constrain the context, the step context between the current step to the next step. So what you're going to constrain is here is that, so for example, when you do like the execute the add inside this step, so in the next step, the code hash will be still remain the same because you are not calling another smart contract. And then the program counter will increase by 1. So like the PC prime will minus PC minus 1 will equal to 0. Then the stack pointer is going to, stack pointer will be equals to SP plus 1. That means like actually, because we use the stack pointer starting from the 1024, we're just going to reversely add. If you increase the stack pointer, that means the stack is shrink by size 1. So because inside the add opcode, you pop 2 elements from the stack and push 1 back. So the stack actually shrink by size 1, so that the next stack pointer will be equal to the stack pointer plus 1. And then the gas left will actually equals to the gas. The next step, like gas left, will be decreased by 3 from the current gas left here. And then also, you notice that this here, we need to also multiply the S add here. So because the constraint, the context transition will be also specific to every opcode you executed. So for different opcodes, the step pointer may have like different changes. And then also for like the gas, also the gas cost for different opcodes will be different. That's why you need to multiply the current selector for this opcode as well for those constraints for the context transition. Okay, the second step is we need to verify the opcode is actually read from the contract and correctly and execute that. That means like you cannot execute arbitrary opcode at current step. It must be, for example, given the current program counter and given the code hash, you must execute the opcode add. You cannot execute the opcode multiply here. So this is the second thing to verify the opcode. So how we're going to do that is that we're going to introduce a lookup table. We call it a bytecode lookup table. So let's take a look at what inside this bytecode lookup table. Your first column, you have the code hash, and second, you have a tag, which indicates whether it's whether this row will be the length or the actual byte from your bytecode. And then there's an index to differentiate the different index inside your smart contract. And then the value will be the actual value that you have inside at every byte or the length here. And then there's one more column, it's called is opcode. So that indicates whether it's an opcode or it's the data that you're going to push. For example, let's say push 1, so that then you push 1 byte into your stack. So the next byte will become a data you're going to push to that. So this is opcode is going to indicate whether it's an opcode or not. So we're going to load. So for example, let's say we have like 2 smart contracts here, like with different code hash. So for the first like a few like the rows, a few rows will be corresponding to the first smart contract, and the second part will be like another smart contract here. So you're going to load all of the contracts that are executed inside one transaction or inside one block or a batch of blocks. So all need to be loaded into these tables. So if you given like you have this table, so that means like let's assume this table is a ground truth, so that it's correctly loaded inside these tables. After that, then you can put in back the event circuit. So what it's going to do constrain that opcode is executed correctly is by doing a lookup, given the code hash, the current program counter, and then like the current executing state you're going to execute. So you're going to find the correct entries here. So basically you look up a tuple into this bytecode lookup table by adding like code hash inside the context register. The byte is indicate like we're loading the byte, not the length. And then the program counter, the current opcode you're executing, and then the one is means like we're executing an opcode, not a data here. So basically you can look into that, and if you find a match inside the bytecode lookup table, that means you're executing the correct opcode at the current step. Any questions so far?
So in this case, the address of the contract that's executing does not matter at all. It's only that the hash of the bytecode of that contract, right?
Yeah, that's a very good question. Yeah, so at the current step, like yes, that's correct. We only need to care about the code hash here. So in fact, there's like one more step I haven't like added here is like before you're executing the transactions, like there will be a step 0. I'm going to initialize, say like I'm executing an address, like this is the callee address. And then you're going to see like inside of this callee address, I will going to have like some constraint that asserts that the code hash is actually loaded from that account object corresponding to the callee address. Okay, so if there's no more questions, like I'll then continue. Okay, the third thing you need to constrain inside the step is that you're going to handle the stack memory and storage operations correctly. So this is like a more complicated cases here. But the approach is quite similar to when you constrain the bytecode, the opcode is correctly, is that you introduce another lookup tables. So here we call the RW lookup table for all the read and writes you happen inside the execution. So this is like what the RW lookup table looks like here. So first, like in the first column, as we say, like this is RW counter, which already see that inside the step register, step context here. So it is like a unique counter for array operations. So like this means like it's grow like by 1 each time. So although like I'm not sorting by the RW counter here, but usually like if you sort that, it will be see like this should be 1, 2, 3, 4, like up to like all of operations you have inside the execution trace. And then second is a tag. So they're going to indicate whether it's a stack operations, a memory operations, or like account operations or account storage you're going to read and write. For the stack and memory, you're going to differentiate like done by the core ID, as I mentioned before. But in the multiple different cores, you can use the same address, but like they will be corresponding to the different values. And then like the address will be like the similar things. Oh, and then for the transactions, for the account things, like you're going to have the transaction ID. So differentiate like what's the initial value, because before you execute one transactions, like you are going to, not going to like permanently write those into the storage as they could be reverted in the future. That's like when you like indicate the transaction ID, that means you know what's the initial value you have inside the storage. And then the next column will be address. So for the address in the stack, it will be like just a stack pointer. So the maximum value would be 1023. Actually, if it's 1024, that means the stack is empty. So the first element you can write into the stack is 1023. And then like the next element you can write into is like 1022, like so on and so forth. And then for the memory, it's like a memory address you have, like it's similar to the definition inside the it's like a byte addressable memory address here. And then for the account, you have like this account address here for that. And then for the storage part, it's a little bit more complicated. So for each address, you actually have a few tags associated with that. It can be nonce, the balance, the code hash, like I remove some of the things because of the space. So there could be like the code hash and then the storage root. They all can be read from like associated with this account here. And then for the account storage, then it'll be like a little bit more complicated. You have a storage key, which is a 256 bits value you have. And then so that into break down into two parts, like the key high and the key low. So each will represent for 128 bits. They're going to use for the storage key column. Actually, that's 2 columns. And then the next column will be a read or write. So indicates whether this is a read operations or it's a write operations. And then the last part will be the value here. So the value for the stack and the storage value, it could be it's 256 bits. So you need to break down into a high and low representation for that. And for the memory, it's like actually it's a byte here you're going to put into the associated with the memory. So this is like what you have inside an other lookup tables. So if you look at it into that, like each row here inside other lookup table correspond to a stack memory or storage read and write operations. And then so after we have this, say like if we trust this table is constructed correctly, so it means like inside the EVM circuit, if we find a matching record inside the other table, then we can assume that the stack memory and storage operations are done correctly inside the EVM circuit. So let's simplify this other lookup table a little bit and then just illustrate here how we did inside the EVM circuit. So basically, you're going to do a lookup. Say I have this current stack pointer and then the current value. And then basically, you're going to see I do a lookup. And then I find a map which pop the word A from the stack and then at the 1022 stack pointer. That means like I pop up the correct stack value from the stack. And similarly, after we did the calculation here, we calculate A plus B will be into the C word. Then you're going to use the stack pointer, and then you can add actually some operations. You can see I push the word C into the stack pointer as a SP plus 1. So assuming the SP initially is equal to 1022, and then you can see I do a lookup with the word C, and then at the stack pointer at the address of SP plus 1 from this register, and then it's a write operation here. So basically, you say I did a write into the stack, and then that's going to also match to a record inside your RW lookup table. Any question for this part?
Yeah, I have a question. So, how do you build this lookup table?
How do I prove this lookup table?
How do you build it? So you get some traces and you translate those traces to the lookup table, and then you verify those traces based on the lookup table?
Yeah, that's a good question. So how do we build this lookup table? It's basically actually when you're executing the executing trace. So our executor is a fork of the GoECM. So inside the GoECM, you have a debug trace module. Basically going to do the record a lot of things, including the current opcode they're executing and then the stack you are going to do. So we're going to basically, the first step when we feeding into the witness into this zkEVM circuit. So you're going to parse the executing trace from the debug transaction inside the GoECM, and then you're going to parse them into for example, each opcode, what operation it does into the stack or memory or storage, and they will create a record and they're going to match to a row here inside the RW lookup table. So that's how we when you parse the executing trace from GoECM, you can basically create those records and feed into the RW lookup table.
Okay, cool.
Okay. Any other questions?
Yeah, how did you prove that this table is exhaustive? I mean, there is no way to basically create an opcode that bypasses those rules.
Yeah, I think that's a very good question. So I think so first of all, the next step I'm going to say how we constrain those lookup tables as those lookup tables are constructed by us. So if you're taking example here for the other lookup table, I just briefly answer your question, and then we can talk a little bit more when I finish the constrain the lookup tables. So here, so you can think so the zkEVM here, it also does some part of the constraint into the lookup tables. For example, it constrains that you need to have if you want to pass the check for your proof. So it means the write into the stack here. Actually, the word C has some relationship between with the word A and B with the word C. That means you need to add these two words and then write back to the word C here. So the EVM circuit does like the sum of the relationship between different read and writes. So that means like if you don't find a match, it could be either wrong inside the EVM circuit or could be something wrong inside the other lookup tables. That means like if, sorry.
Go on, go.
Oh, okay. Yeah. And then so, and also like the stack pointer here. So if you like at a different address, like say I modify the word C here in the other lookup table, then that means the EVM circuit is not going to find a match inside the other lookup table. Then it means like the proof is failed. Or like if you modify the address here, then the stack, it means like, so inside EVM circuit, when you do lookup, it has to be the current stack pointer plus 1 when you do the lookup. So if we modify this, you're not going to find a match here. So that means like so the EVM circuit alone adds some constraint into the other lookup table as well. And then another thing, additional things that we're going to do is we're going to also add extra constraint onto the lookup tables, because these are not fixed columns. So these are all advanced columns, which means like you're feeding like themselves by the provers. But we also need to add certain constraint to constrain that the lookup tables cannot be constrained arbitrarily. And then one last thing like we're going to do is like, since we have the global counter, we're going to check like all of the rows you have inside the other table has been covered by the lookup inside the EVM circuit. That means like you cannot have an additional rows here inside the other lookup table that is not queried by the EVM circuit. So we think like by combining all of these constraints, you can prove that the other lookup table, you cannot have another way to build the other lookup table. Although you can like, definitely you can change the sequence of the rows, like those should be like no, actually there's constraint actually constrain the sorting of those rows inside the constraint associated with this other lookup table. So actually you can prove like this is the only way you can build this other lookup table. Does that answer your question?
Yeah, more or less. Thank you. Yeah, I need to like go back to it. I think just to be more about it.
Yeah. Yeah, I think this is like a very tricky part. I think when constraining the zkEVM is like so there's a lot of different relationships between different circuits, and then can we are these like the constraint sound enough to cover like to prove that those lookup tables can be like the uniquely constructed like that, and cannot be put into any invalid records inside that.
Yeah, sure. Thank you.
Yeah. Okay. So let's go just jump into the next section. It's like so we already say like because those lookup tables are constructed by the prover, so we need to constrain those lookup tables cannot be constrained arbitrarily. So let's think back like so take a bytecode table as an example. So what assumption when we make when we do the lookup into the bytecode tables, we make certain assumption that the bytecode table is constructed correctly. So the first thing is like the bytes loaded into the table are the same as the bytes like stored in the smart contract. And the second is like its opcode is correctly indicates whether a byte is an opcode or not. So let's like take back this bytecode table examples. So we want to prove like this table is constructed correctly, cannot be like do something wrong. So what you're going to do is like you're going to add additional advice columns that are going to help you to prove this lookup table is correctly constructed. So basically you're turning into a bytecode lookup table into a bytecode circuit by adding like a few additional auxiliary advice columns are going to help you to prove that. So what proof we're going to do? So for example, let's say we need to prove the code size is correct. So basically you need to have like a reverse index inside the length for all of the bytes here, and then prove like the number of rows you have for the byte is the same as like you write into your length row here for this bytecode. And then second, we want to prove that its opcode is constructed correctly. So first you just say when this opcode is a push opcode, then we have like an additional column called a push R index. It's meaning like how many bytes left going to have for the next few rows will be the the data, like it's the non-opcode, it's actually the data. So you're going to first have constrain this push R index is set correctly. Corresponding to like it's push 1, then this value will equal to 1. It says push 32, then this value will be 32. And then given like you have this push R index column here, then you're seeing like this is opcode and has to be 0 if the previous row inside the push R index is not 0. Then you can construct, you can say like this is correctly prove like that this row should be is not an opcode. And then also you need to constrain like this push R index, the reverse index is reduced by 1 if it's non-zero here. Like if the previous row is not 0, then the previous row minus the current row will be equals to 1. Or if it's 0, like that, then it can be always 0, like copy along. Okay, so with like these 3 constraints combined together, then we prove this is opcode column is constructed correctly. And then how do we constrain? The last piece is we need to prove this bytecode table is we need to constrain the code hash. So this will be a little bit more complicated. So we're going to have another lookup table to help us prove that. And here, like inside our like the zkEVM, like the designs, we also replace this code hash into the from Kachak to Poseidon, so that it can reduce a lot of overhead you have with the Kachak, because Kachak is really complicated when you write into the zk circuits. Like if you have everything to construct, like to build inside the using Kachak circuit, it becomes a bottleneck to the whole zkEVM. So actually replace that with the Poseidon hash table, Poseidon hash. So basically you're going to do like you construct the Poseidon hash tables. And then you're going to break down into the trunks and then do the lookup to that. So each row will do like you taking 2 inputs, and then the hash is not the current output, it's the final output. So I match with the final output. And then you have like the indicator, like how many bytes left inside that. And here, because each value here is a byte, but for us, like the value can be like up to 254 bits. So we're combining like actually multiple bytes here, and then do a lookup into the value 1, and then the next I feel like and then match into the next value, like value 2. And then this is the hashes indicate like it's matching with like the one certain like a hash here. And then the bytes left is meaning like how many bytes you're going to do like the hash inside the Poseidon lookup table. So basically do like a lot of lookups into the Poseidon hash until you prove that until you finish like up to the 0 ones. And then that means like you put all of those things into the bytecode hash, into the Poseidon hash tables. Then you can prove this hash is actually correctly calculated from all of those values bytes you listed here, associated with with this contract here. And then so for this Poseidon hash tables, you also need to add additional columns later to constrain that those hash are these hash are actually calculated correctly by apply all of the value you have inside your Poseidon hash circuit. So basically, there's some additional columns here to help you to prove that prove the Poseidon hash is calculated correctly. Any questions so far for this step?
Can you explain why? I don't get what is the point of input 1 and input 2? Is this just to have more amounts hashed per row?
Oh, so this is actually the definition of the Poseidon hashes. You can take in multiple inputs and then apply that. It could be like 2 to 1 hash, or like it can be like 4 to 1, like 8 to 1. So you are choosing like 2 to 1, like taking 2 inputs once, like, and then generate the update the hash, and then next time you can squeeze in another like 2 inputs here.
So are you like hashing the entire all of the bytecode or only parts of it? Or are you like
all
combining?
of the. So actually, so this hash there'll be some accumulating hash like this, like the current like hash will be some state stored inside that. But this hash here is only to help you to address like the corresponding to the output here. So it's the final output hash. So that doesn't mean like this hash is equal to when you're hashing to value equal to this hash. But it is like a unique identifier for a bunch of hash like happens associated with a single hash block, you can see.
So then there should be another constraint that checks that all of those hashes are the same as the accumulated one at the end.
Yes, yeah.
Okay.
So you see, like for example, like these rows like could be like all the same, and then there's like accumulated hash, and then your constraint at the last step will be like the same in the bottom. So I make sure like the hash here is calculated correctly. And then for this part, if it's not, the best life is not 0, then it should be equal to the previous row.
All right, thank you.
Okay, so let's also like jump into the RW table, which address like a little bit problem. So because RW table is actually more complicated than the bytecode. That's we made like the multiple assumption, I think, to the RW table. Here, like I think there's 3 assumptions we made. So first of all, so remember like when we do like lookup from the EVM circuit, we just only assume that all the values are pushed and then write and read correctly into a certain records inside our RW table. But we assume we make assumption that the values that we read from an address is actually the same as the previous value you wrote into this address. So that is we didn't we only assume like a single records here inside the RW table, but we didn't assume the kind of the continuity inside the RW table. So this is like one assumption you need to check for this RW table. And then second thing is like when we expand the EVM memory into like a larger size, the memory will be all initialized to 0 like that. So that means like if you want to read to a memory like the first time, you should be always read to the 0. And then the third thing is like assumption we made is like the initial value read from the storage slot is correctly loaded from the global state tree. That means like this is like some assumption like you won't be checked from the EVM circuit side. So EVM circuit side is like after you read certain value into let's say into the memory or into the stack, then you do some calculations and then you write back to the stack or memory or storage. So it just only proves the relationship between like a transition from the current read and then the next write, but it doesn't like some initial value. It doesn't constrain inside the EVM circuit. So let's bring back like the RW table, which is also a little bit simplified. So let's be easier to just illustrate, but actually circuit will be more complicated. So the first one, when you created this RW lookup tables, you're basically this is the records you parsing. When you parse from your GoECM execution trace, you're getting like a record say like I do some of the write to the stack and read something or write something to the memory, and then you have like a bunch of records when you're passing through your execution trace. This is like the trace records you have. And then the first thing when we fitting into the RW circuit or RW lookup tables, you're going to sort them by like a certain rules. For example, we want to sort first by different tags, by different sections. If we say like all the stack, all the memory, all the storage will be sorted into different sections. And the second thing you want to sort is like sorting the address. And then the third thing is by sorting the RW counter here. So that means then you can prove that the value you read is the same as the previous write here value. But this is when you sorting those rows, it's just going to help you to prove this read after write property from those other lookup tables. And then remember that because we're using the lookup argument, so the order inside the lookup tables or inside the circuit, it doesn't matter. It just only say if I can find a matching records inside the table. They can be in the first row, it can be on the 100th rows. It doesn't matter. It just need to say I find a record, a matching record inside the lookup tables. So after you sorting that, then you can constrain this read after write property. Is that if the current is a read operations, that means that the value you read should be the same as the previous rows. As long as so this is also makes simplify a little bit. It means it's not the first row for this address. If it's the first row, then have a separate logic. So for example, for the memory, the first row, if it's a read, then it has to be the 0. I mean, see the memory is correctly initialized to the 0. But for the stack, if it's the first row is 0, then it means like it's an invalid trace. You need to say like the first row to the stack, it must be a write, because you cannot pop like from a current one stack address without pushing a value previously to the stack address. So they have certain constraint like associated with the first row inside each address. And also the next thing is you're going to check is like the certain columns are valid. For example, the RW can be only 1 or 0. The tag here can be only like certain tags like stack, memory, or storage. Like it can be like only certain tags. And also you need to see like when it's a stack, the address can be only like among 0 to 1024. You do a range check if tag is 0, if tag is stack. And then the last thing is you're going to constrain is like if the sorting is done correctly. So it means because when we constrain this read after write property, we relying on this all the rows are sorted correctly. So you also need to constrain that all the rows are sorted according to the lexicographic order that you define with this tuple here. That means like a tag need to be like less equal to tag next. If they are same, then the address has certain property. If the address is the same, then other counter need to be strictly smaller than the next row. So with these things, like then you can constrain those things. And also, like I forgot to mention, like if it's a storage, if it's an initial read, then you need to also do a lookup into the Merkle Patricia table, like called MPT table. So I'm going to look into the MPT table. They're going to constrain that this is actually the correct value you read from at a certain snapshot of your state tree. Okay, so any questions like up to this point? Okay, if not, like the next section I'm going to talk about like how we constrain the input here. So previously we all like talk about like the constrain the tables, the EVM executions, but we didn't say like how we load those input correctly from the public input. So this is, I think, almost like the last part I'm going to cover inside this talk. So first of all, I'm going to talk about what's the public input we're going to put into the L1 smart contract. So we're going to put like actually, I think I forgot to add one thing. Is like the data we roll up is for example, the old root, the new root, the block header, and then all of the transaction data. But for the transaction data, like for each transaction, you're not going to put everything into the catch check and then use like the final hash result as input. So basically, you need to first do the catch check on the transactions, so you can calculate the transaction hash for all of transactions inside this batch, and then you can hash them like all with like different transaction 0, transaction hash 1, and then you calculate all of the transaction hash, and then and then you concatenate them together and then do a big catch check here. So using this final public input as the catch check as the results. So and then we inside the zkEVM circuit, so we have like a special circuit called a public input circuit. I'm going to import this public input hash and verify. So first, you're going to do is verify the catch check hash is done correctly, and the second, you also need to expand this like back into those fields, and then provides those inputs to the block header, block tables, and then transaction tables. You can provide the block headers and some other informations, and then old root, new root, and then the transaction hashes. So let me show you like what this public input circuit looks like. It'll be like one instance column. That's basically is the public input you have. Because we're using the catch check hash, so it's 256 bits. You have hash high and hash low, like 2 elements here, and then the next row column will be like all the values you're going to use to hash those hash to derive this hash output. So you have like old root, new root, like the block headers, and all of transaction hash. And then what you're going to do is like in the public circuit, you're going to basically hash those values. So here, actually, I simplify a lot of things because when you do the lookup in the catch check table or catch check circuit, you also need to expand them into the bytes. So here we're assuming like these are the direct values, but actually when you do the hash, you need to break down into the bytes So it'll be like additional advice column here will be the expansion of those values into the bytes. And then you use the bytes, like the array, to look up into the catch-up table so that you can prove this hash is calculated correctly. So actually the public input is derived from by hashing these values here. So for the block things, it will be simply quite simple. You basically do some permutation check, copy those values into a block lookup tables. I'm going to construct like a small block lookup table, and then those block lookup tables can be then used by the EVM circuit when you're trying to load certain information from your block. As if you want to load block hash or you want to load timestamp or those numbers, it can be provided by this block header here. But for the transaction, it will be a little bit more complicated because we only include the transaction hash here. So we need to expand them into more like the detailed transaction data. So I'm going to have this transaction table in the circuit. So first thing to do within the transaction table is that we can copy this transaction hash from the public input circuit. So this is like what a transaction table looks like. You have like the transaction, you have 4 columns. First column will be the transaction ID. And then second, you have a certain tags. So you have like the nonce inside of this transaction, the gas cost, and then and some other things like the gas tips or other like the data you have from your transaction when you're encoding your transaction, and also along with the signatures. And then these two are actually the additional things that is not included inside of your transaction data, but it's transaction signature hash and transaction hash. And then the last part, and then second, you're going to first load certain the transaction header here, and then the last part will be the actual transaction call data, which you're going to differentiate them by using the index column here. If it's the first transaction, the call data, what is the first byte of the inside the first transaction's call data. So basically, then you need to build a relationship between the public input circuit to your TX table. It's basically you need to do a permutation check, like a copy constraint. Say this transaction hash. Oh, sorry, it's not this one. It should be this cells. Because this cell is the actual value. So basically, you copy the transaction hash into this cell here. That means it can it is imported from the public input circuit. Then the second thing is we only import the transaction hash you have from the public input circuit. Now we need to prove the next thing you need to prove from the transaction table to the transaction circuit. You need to prove the transaction hash is actually calculated by using all of fields you have inside your transaction table from this part. Basically, you need to say after I do the RP encoding of this part of data, and then do a catch-up hash, you actually derive this hash value here, so that I can be sure that this value I put here is a correct value you have inside the transactions. So that's why the next step for the transaction circuit is you need to connect to an IRP table that's going to help you to verify the IRP encoding of the transactions and then the transaction hash. So now we have another additional table here, or the table or slash circuit. So you have a type is all you can do for this IRP encoding is going to encode for the transaction hash. So first of all, you have the ID. Basically, this is the transaction ID corresponding to the same transaction ID. And then you have this specific IRP tag that's going to say if this is a prefix going to encode some of the lengths of your IRP lengths, and then certain part will be TX nonce, the next part will be TX nonce. So basically you have some auxiliary data you here for IRP tag encoding. And then the next column will be the bytes, every row will be a byte. But what you have here inside your TX table is the value, which is by combining the multiple byte here into constitute the value. That's why you have an accumulated value by accumulating multiple rows of bytes into a single value here, so that the TX table can do lookup into the RP table to prove that actually this is encoded correctly from this RP table. And the RP table definitely we're going to add other constraint to constrain that this RP encoding follow the RP encoding rules to do that. And then another thing IRP table is going to do is like you're going to take all of the bytes, you expand it from the IRP encoding, and then do a lookup into the catch table to prove that this transaction hash in the final row here is actually the correct hash results. And then you can then connect them from the TX table into your IRP table, saying that, okay, now I need to connect this transaction one nonce tag and then with the nonce value into this row, which we have here is like the accumulated value of those different few bytes, which constitutes this nonce here you have. And then for the rest of things, you also need to do is the similar things. And also don't forget that we also need to constrain all of the byte, all of the core data bytes are also appeared correctly inside the IRP table here. And then finally, then you can say this transaction hash by looking up into this IRP table, you find the matching hash here. So that's why we can know that the transaction hash is actually correctly derived by hashing those values you have from all of these fields you have inside the transaction table. Any question in this part? Yeah, this is a little bit complicated, but I think I'll just move on. So the third thing you need to verify inside the transaction circuit is actually the signature is calculated correctly inside the transaction. So you're going to verify the transaction SIG hash, the signature hash, and then you need to verify the signature is derived correctly. That means that we also need to introduce one more section inside the IRP encoding. So let me explain a little bit what's the how you calculate the hash here if you're not familiar with the EVM. So basically you're going to do IRP encoding on all of the part. Without the signature part, you need to encode all of the value here and then the core data value here. And then you do IRP encoding and then you calculate a catch hash of all of the bytes you have inside IRP encoding here. And then use that to sign, and then you can get the signature VRS here. That means similarly is that we need to to check the value. You need to expand those encoding of the signature part of IRP encoding here by having those values copying to this this part of the signature TX signature hash part, and also copy the core data here. Actually not copy. Actually, this is lookup into here, and then finally inside the IRP encoding table, you can look up into the catch, and then you can check whether the hash, the TX SIG hash, is constructed correctly by applying all of the IRP encoded table, IRP encoded bytes here. So the next thing inside IRP table is you also need to have all of those bytes and then do a lookup into the catch and then do a output check the hashes calculated correctly. And then the last part is that given you already proved the transaction SIG hash is calculated correctly, and then you have all the signature you have, so you basically need to do a lookup into the VRS and the hash, and you can do a recover your caller address, so that you can make sure this is actually invoked by certain caller. So actually there will be additional entry inside the TX table, which is the caller address. That is not going to participate inside all of your the TX transaction IRP encodings. That's some additional data we can have inside the TX table, but we also need to constrain that the caller address is correctly calculated by using the ECDSA things to recover the caller address. Okay. Yeah. So, any question up to this part? Okay, so if there's no more question, I'll move on to the final last pieces. Let's say we put in all of the things we mentioned previously, putting all of them together, and then we'll have to show you what's the zkEVM architecture we have from the school side. So first of all, in the beginning we have the event circuit as I described previously. Oh, do we? Oh, sorry. There's one question from the chat. Is do you support multiple transaction types? Yes. So we're going to support multiple transaction types, but right now we in the circuit we're only having the IRP encoding for the legacy transaction type. We're going to add in like to support this dynamic fee, like basically the EIP 1559 transaction type. So we're going to support all different transaction types. Okay, so let's take a look at the zkEVM architecture. So first of all, you have the EVM circuit that's going to constrain your step states and some basic opcodes. I say like add, you can directly constrain that inside your step slot. And also you need to constrain the transaction from the current step to the next step and all of the stack read and write operations. Then there are certain opcodes that are not going to be zk friendly. So for example, those are bitwise opcodes, the and all things. So that's going to do is you have this is the fixed lookup table. So you basically pre-compile some of the all of the possibility for doing the and, all, and the XOR opcode, and you encode them into lookup tables. So when you're trying to constrain inside the event circuit, you can just do lookup into those fixed lookup table. And the second, there's some complicated opcodes. You're going to also offload to some side circuit. Here, a lookup table here, for example, the exponential, and then the catch check. So these two will be also offloaded. So it's too complicated if you include everything inside the EVM circuit here. So you're basically relying on opcodes and then having some other circuit to constrain those lookup tables here. And then so you want to handle the stack memory and storage operations, you have the RW lookup table. And then you also need to constrain like when EVM, when inside the EVM, you want to load certain things like from the bytecode, from the transaction call data, and from the block information. So you have like 3 additional lookup tables you have to load from that. Now we need to constrain the lookup tables. For example, the exponential lookup table, you have exponential circuit to constrain the value here is correct. And then for the RW lookup table, you have the state circuit or RW circuit to constrain here. But RW circuit, as we mentioned before, we need to look up into this MPT lookup table to constrain the first read, and then the write will be updating your Merkle, your state root here, your Merkle Patricia tree correctly. So you also need to do a lookup into a Merkle Patricia tree table. And then so you have like a Merkle Patricia tree circuit to constrain this Merkle this lookup tables. And then we're also using we also modify a little bit of the existing EVM state tree. We change it into a sparse binary Merkle Patricia tree. So and then with the Poseidon hash, so going to reduce like some overhead by using all of them in catch-up. So that's why the Merkle Patricia tree circuit need to constrain this lookup table, but also relying on the Poseidon lookup table, which will be constrained by the Poseidon circuit. And then next is going to constrain the pub inputs. So the pub input circuit will provide like the transaction hash to the transaction lookup tables, and also provide that into the block lookup tables. And I'm also going to like constrain the old root, and then the final new root is the exactly same matching inside your Merkle Patricia tree table here. So constrain like provide these values from this public input circuit. And then you have like this catch-up circuit going to constrain the catch-up tables, bytecode circuit constrain the bytecode tables, transaction circuit will constrain the transaction, but relying on the IRP tables, which are constrained by the IRP circuit. And also they have the also relying on the signature tables, which are going to be constrained by the ECDSA circuit. So with that, this is constituted of like the entire zkEVM architecture. Do you have any question for that?
Do you guys support create too, or no?
Yes, we support create and create too.
Okay.
Okay, so and then all of this work actually we're doing like in the open source, collaborating with like Ethereum Foundation, the PSE group from the Ethereum Foundation, and also like other many more open source community members, as well as like the Halo 2 is also an open source proof systems. It's like a bunch of like the guys who contributing like from the ECC team, Zcash team. They contribute and wrote this very great Halo 2 libraries. So these are all the people, like not all of people, there's many more here, and then actually the members are still growing. So I want to credit all of things to the community members. And then thank you. That's all for my today's presentation. Do you have any other questions? Maybe in general, like general question.
So a bit of a high-level question. So what's the right way to think about the sizes as you go through sort of the different stages of expansion? Like, what's the different way to think about the size of the input program, the size of the trace, the size of the circuit, those kinds of parameters?
So you're seeing like what's the size of the circuit? So the size of circuit actually are constrained. The size of circuit are constrained like the prefix. So I'll say like the if you're going to say, so for example, all of the circuits you have, all of the circuits you have here, they're all going to be paired to the same size. So same size of like the rows inside each circuit or lookup tables. They'll be all paired to the same things. So it'll be easier to constrain and connect between different circuits and tables. And then the size of circuits is also configurable depending on, I guess, a trade-off. If you have a larger circuits, then you can support more gas costs you have inside your transaction inside the layer 2 blocks. And then but like if you have larger circuits, then it means like your proving time will be larger. So right now we're considering like for example, all of the circuits here is like 2 to the 18 or 2 to the 20, 2 to the 20 like the circuits, which can support like a few million gas costs inside the layer 2 blocks. But we're also like still doing some playing with the trade-off. If we have like more better optimization, maybe we can have larger circuits. Does that answer your question?
I mean, I think it does. I guess I'm sort of, trying to ask about the kinds of bottlenecks that are likely to arise. Right? So if you think about the variety of bottlenecks, what do you typically think about?
Yeah, I think that the bottleneck is first things like I think would be the inside the EVM circuit, because the EVM circuit is the main processor circuit. So it has like it uses like most of the rows you have. Like if you do like we do like some mocking on some larger blocks, and then we found like the EVM circuit is the most constrained circuits. And the second could be the catch check and then some of the ECDSA circuit, which going to have more constraints associated with that. So this is like our current like things like of the most constrained circuits inside this. Okay, so if there's no more questions, I'll give the time to Jordi and Carlos, and they can present their designs from the Polygon Hermez zkEVM design.
Hi everyone, my name is Carlos Matallana. I'm a member of the protocol and integration team. I'm the team lead at Polygon Hermez. Our team basically is in charge of writing the smart contracts, writing the ROM, which is basically an interpreter of the EVM, and also writing the specification that the zkEVM follows and implementing. So today we're going to see the language that we use in order to implement the zkROM. And this language is called zkAssembly. And based on this language, we implement the zkROM, which is the EVM interpreter. Later on, first we'll explain a little bit the zkAssembly, and later on we will explain, and we will see some snippet code of how we implement the EVM. So this mainly all the sections that we're going to cover in this talk. At the very beginning, we're going to talk about the differences between the EVM and the zkEVM that Polygon has. One of the most important is the state tree. Also, we'll see the difference between the memory regimes that we can handle. Then I will introduce this new brand language, which is the zkEVM. Just to remind you that the zkEVM is a general purpose language that you can use to write anything. In that case, we use it in order to run the zkEVM. But any developer could take this language and write the code that they want. We're going through all the registers that are implemented. We're going to see a diagram and instructions, and later on we see some small example. This small example will be basically an introduction in order to see how we implement the zkEVM afterwards. Okay. So let's start. If you are familiar with Ethereum, you may know that the Merkle tree that Ethereum uses is a modified partition Merkle tree. The main properties that they have is they have for each level they have 16 childs and the user function, which is the KICA 256. And there is one important thing here, that which are the values that are inside a leaf in the Merkle tree. And they are basically the value is in fact a KICA of the RLP of an Ethereum account. And an Ethereum account is composed by the nonce, the balance, the storage root, and the core hash. And the storage root is basically on all the storage that an smart contract has and is coded into another modified partition of the tree. This is how the tree looks in the EVM. But how the tree looks in the zkEVM? We have small differences over here because our tree is a binary tree. It's a sparse Merkle tree. It's binary. We have 2 childs for each level. We use a different hash function. As we saw it, EVM uses a KICA, and we use Polygon. We use Polygon because it fits better with the thorough knowledge. Okay, and regarding the value, and this is very important, notice that we do not add all the parameters in one leaf in the Merkle tree. We separate the parameters in different leaves in the Merkle tree because it's more convenient to us in order to perform fastest computations. Okay. Notice also that the value inside the leaf, it's composed, it's an array of 8 values. And each value is a Goldilocks prime field number, okay, which is basically this number here. Okay, this is very important. We will see afterwards because of the registers of the CD assembly that it's using. Okay, since we need to deal with EVM numbers, and the EVM numbers occupies basically 256 bits, we need these 8 field elements, and we take only the less significant part of this print field number. Okay, so at the very end, we're dealing with 256 bits, but internally are 8 elements of a Goldilocks prime field number, and we use the 32 less significant bits. Regarding the memory, we use a context-based memory. As you may know, in Ethereum, every time that you perform call, delegate call, create to, you need to create a new context with its new stack and its new memory, and you fulfill it depending on the call that has been done. In order to handle that, we are going to implement a zkEVM memory, but with different context. And you can switch the context very easily with just a register. And you can move inside the different memory regions of the context very easily, again, with just a few registers. What are the differences between the memory regarding the zkEVM and regarding the EVM? Well, basically, the memory and the EVM are its slots, and these slots occupies 8 bits. What we have in the zkEVM are memory slots that occupies basically 256 bits. So we kind of need a mapping between the EVM and the zkEVM that we need to handle. And also, in order to handle that, because if the bytes are aligned in 32 bytes, it's really straightforward to take 32 bytes of the EVM memory and then put it in the zkEVM. But what happens if there is some misalignment over there? What happens if we need to take the first part of the slot in the zkEVM and write some number over there, and at the same time take the second slot and write some number over there? This is a little bit tricky, and we have a special state machine in order to deal with that, which is the mem align. And regarding the stack in the EVM will be exactly the same that we have in the zkEVM. Since the stack in the EVM it occupies 256 bits, we mimic this kind of stack in the zkEVM because we also have 256 bits. Okay, but also since we have a lot of space in the stack, I would say that the first 1022 slots of the stack will be used in order to mimic the stack of the EVM. The rest will be used in order to store the call data, and we'll read the call data from that, and we'll interpret the call data from that. Okay, so now we're going to introduce a little bit this assembly language. We're going to see all what is available in the language, what is available for us in the language. Basically, we're going to see which are the available registers that we can use, and we're going to see what are the available instructions that we can use. This language is called zkAssembly because at the very end, it's like writing assembly at low level in a CPU. Okay, but here, later on, this assembly is converted into polynomials, and that's why we put the zk in front of the assembly. So first of all, I'm going to go one by one through the registers. I'm going to comment on them. We have, it's important to mention we have two types of registers. There is one registers that are composed by 8 elements, and each of one of these elements is a Goldilocks prime field number. As you may remember, when I mentioned the zkEVM state tree, I told you that we are in the value, we are inserting 256 bits, but they are divided in 8 elements. So that's why we have this kind of register. So first of all, we have generic registers that you can play around, which is A, B, C, D, and E, and all of them they have this kind of array of 8 elements. We have the state root, which basically will be the state root of the method tree, of the state tree. And we have the rotate left seek, which is, I would say, a useful register in order to avoid to use state machines afterwards. I mean, it's a register that optimizes a little bit the code. We're going to see now the rest of the registers, and basically the rest of the registers are just only one field element. The first ones are the zk counters. What is the meaning of the zk counters? The zk counters are basically the resources that the prover has available. I mean, we cannot waste all these resources, otherwise the proof will not be generated. And you can see this kind of resources as the gas in Ethereum. So instead of, we also have the gas, of course, in order to mimic the VM, but also we have this kind of zk gas, you could say. We have another register, which is the context. I already mentioned that when I introduced the regular versions of the zkEVM, and it basically helps us to move from the memory regions. We have the stack pointer, which also helps us to move in the memory regions. We have the program counter. The program counter is a register that will tell us in which position of the smart contract bytecode we are going to read the following bytes. It's important to notice here the program counter is regarding the smart contract that we are reading. The gas register is the available gas in a transaction. the zk program counter. The zk program counter is the program counter of the current program that we are running, the zk program, we could say. Okay, so just notice the difference between the program counter and the zk program counter. Also, we have the return register, which is basically utility. It's a useful register in order to perform some jumps and returns in assembly. We have the step register, which is basically all the instructions that we are. It has all the counts of the instructions that we are running. Max memory, which basically tracks the max memory that we have, and the hash position. We will see later on how the register is used. Okay, so which is the process of using this register? So basically, what we could do with the registers. Okay, what we could do is we can add, we can multiply, we can move the registers to another one, and basically this is a simplified diagram of what the processor can do. Okay. So at the left you have the input, at the right you have the output. This is just like a state machine. So you have an initial state and you have a final state, and depending on the flags, the final state will change. So for example, if I want to move A into B, so I will have activated the flag in A, so the A will be to this intermediate value, which is up, and this is very important. This kind of is an intermediate value. And later on, if I have the set B register to set to 1, then this up will be loaded into B. Okay, and it happens the same with all the registers that I mentioned before. Okay, now that we know the meaning and all the registers that we have available in the assembly, I'm going to explain all the instructions that we have available. As I mentioned at the very beginning, the zk assembly is a general purpose language, but we use it to build the zkEVM. So some instructions I would say that are thought to be used for the zkEVM. So the first instruction is the memory load. Is quite straightforward. You took some value from the memory and you load that into this middle register. Okay, the up register. And we will see afterwards that we use this free in, that you can put whatever value you want. Okay, but later on there is a state machine behind that assures that this value is okay. So for example, in the mload, what we are doing is we are loading any value that we want into this up through the free in, but there is a state machine, which is the memory, that ensures that this value belongs to this address of the memory. Okay, and this happens with all the free ins that we are using. We can put whatever we want, but also we check what is this value. Memory load, just to load some memory region to this intermediate value of memory store. We just store the intermediate value into memory. Hash key len, and hash key digest. Those three instructions are used in order to perform keycat hashes. Okay. We will see in the slide later on a diagram how this instruction works in more detail. But basically, with hash key, you are adding all the bytes that you want to hash. The hash key len is to close the hash, and hash key digest is in order to retrieve the hash. Exactly the same instructions are used to perform the Polygon hash. And then we have the jumps as any assembly language, I would say. And basically, these jumps helps you to jump to a different regions of the code depending on some parameters. In that case, we have this direct jump. You just put the address that you want to jump and then you jump. This jump negative, it depends on the value, on the intermediate value, which is the up. If it's negative, it jumps, otherwise it just increments by 1, the zkEVM counter. And also we have another one, which is the jump curve. Depending on the up, in fact, we are jumping or not to the next zkEVM counter. Well, depending on the carry. So the carry, you will see afterwards that depending on the instruction that we perform, it could have a carry, so we can jump easily to this address depending on the result of the instruction. Okay, it's just for it's. I would say it's a helper jump. Okay, we have these two instructions, call and return. Well, they are very useful because it performs some computations, and you don't notice regarding these computations. They are basically saving the zkEVM counter when you perform the call, and when you perform the return, it returns to the previous zkEVM counter that you faced when you did the call. Okay, these are very useful in order to navigate through the code. We have this assert, which is basically takes the register and compares if it's equal to the intermediate value of. And here we can see one of the most important instructions, which is basically the storage. Okay. The storage load and later on the storage store, they are basically reading leaves from the Merkle tree that I showed at the very beginning and writing leaves to the Merkle tree. Okay, but this is very important because it modifies the zkEVM state. Okay, just what I want to mention here is that in order to use these instructions beforehand, you need to provide some data in order to compute. In the case of the lab, the key that we are going to navigate through the Merkle tree in order to retrieve the value, and regarding the store, we're going to compute the key, but we also need to provide the value. So we need to be aware that before calling these instructions, we have been set all these registers accordingly in order to write or read the value arithmetic state machine. Okay, the arithmetic state machine, what it does, it verifies computation, basically. Okay, it will be used every time that we need to perform some multiplication, some division, some addition, whatever it needs. Okay, and basically, for example, the addition, you just put the value that you think the division will have, and then you check it with this arithmetic state machine. So you don't compute the division. Okay, you just put the value of the division and then you check that value if it matches, but you check it with a multiplication. The next state machines are subtraction and less than. Basically, trigger the binary state machine. As you remember from the stocks, the binary state machine basically takes two registers and it compares its result to the intermediate comparison. I mean, it enforces that the intermediate value is indeed the register A plus B in case of an addition. Okay, for subtraction, it enforces that the operation is indeed A minus B. Same with less than, sign of less than, equal, so equal and or and it's all. Okay, and the last instructions, as I mentioned when I explained these memory differences, they are the mem-align instructions. The mem-align instructions basically calls activates the mem-align state machines and put it in a way that they are very similar to Ethereum. So we have a memory aligned read, memory aligned write, and memory aligned write 8, okay? In order to be kind of similar to Ethereum, since they have almost exactly the same opcodes, I would say. Well, the state machine basically, just to summarize, I will not go into details, but it takes 2 slots and it compares the value that you write. It's the value that you want to add, and in case of read, it basically takes the 2 slots, takes one part of the slot, another part of the slot, they join it together, and use the value that you want to read. Some checks regarding that value, and what is misaligned, there is some tricky things. Okay, now that we know a little bit which are the registers and the instructions that this zkEVM has, we're going to see a small example of how to use it. Okay? And this small example, we first start from an initial point. And this initial point means that we have an initial memory. Okay, and this initial memory in the context 1, inside the stack of the context 1, we have the 2 first values are 2 and 3. Okay, so we need to, the program, what it does is, it reads these 2 values, they add together, and the result, it is written again in this specific address in memory. Okay, and what we're going to see, and we're going to go step by step, line by line, in order to see what this program does. Okay, this is the initial condition, I mean the initial memory. This is the program, and the result, the final state will be that we write in the stack this 5 here. So, okay, let's start. First, you saw the initial state, the initial memory. So what we want at the very first is to read these 2 and these 3. So what we're going to do is to set all the registers necessary in order to compute the address that I want to access. Okay? And in that case, I want to set the context 1. That would be the first instruction. Okay. Then I want to set the stack pointer to 1. Then I will read the second number, the 3. So now I have here, I would say, the address of the memory set. So what we're going to do now is to read that with log. Okay, so I'm going to perform memory load. And what is the value of the context and the stack pointer? 1, 1. Okay, so we're going to the context 1 and take the second value of the stack, which is the 3. And I will load that in the 3 in. Okay, and the memory state machine will ensure that this value is indeed 3. Okay. No, and we are loading this intermediate value up in A. So we have the flag set A set to 1, and this value will be loaded in the A register. Okay. This is what this instruction does. It takes one value from the stack and it loads in register A. Also, at the same time, we are decreasing the stack pointer. This is for convenience as well, in order to not put this line in another instruction line. We are doing all the computations we are doing just in one line. So at the very end of this instruction, the stack pointer is decreased to 1. And this allows us to do this instruction there. This allows us to read then the 2 values. So here we have context 1, stack pointer is 0. So we are going to read the top value at stack regarding the context 1, which is basically 2. And these 2, we are going to load it into the field. And this is assured that we're loading here, we're loading the 2 because the memory state machine forces us to load these two to the free. And in that case, the op, the field, the intermediate value, we're going to load it into a register B. So the set B, the flag set B is set to 1, okay, and then we add it into this register. Okay, so basically now we have read two values from memory. What we're going to do now is to add those values. So use the binary state machine in the addition mode. And as you remember, the instruction of the addition in the state machine is basically taking register A, register B, and it computes the result that it computes, it is loaded in this intermediate value. And I want to mention again, you can put all the value that you want in this intermediate value in the op, in the free. But in that case, the binary state machine will enforce that this value is A plus B. So we are checking that value. We are not computing that value. We are checking that value. Okay, so we add A plus B and we set it to the register C. And the last step is basically write in the memory. And in this case, we are going to overwrite, for example, the first position in the stack, for example, in the context 1. So we are basically moving the C register, which will have the result of the writing into memory with the mstore instruction. And remember that the stack pointer was, and remember that the context was 1. So we wanted to write that value in that specific area of the memory. Okay, so we have seen the zk assembly code, the registers and all instructions that we can use. We have seen also, I would say, a small piece of code that will be very similar to the zkROM in order to show a little bit the syntaxes. And here I just want to show all the files that we have in the zkROM. So this is basically the name of the files, the current name of the files that we have in the zkROM and all its dependencies. In case that you enter into the repository and check, it's all open source in GitHub, you will have an idea on all the dependencies, and you will have the entry point is the main, and we have this context bar, loading transaction IP. We'll go over these files in the following slide. Okay, now we are going to see how to process a batch. We're going to see the implementation of the ROM, the interpreter of the EVM. But before doing that, I think there is the space, and there is very needed an introduction of how we use the data and which data are we using when we process a batch, and how this data is enforced. In this case, it's enforced by the smart contract. Okay, as you may know, rollup basically works that you need to send some data to the smart contract, which is the availability. Okay, in that case, we have one entity, which is the sequencer that calls the smart contract function, which is the sequence batches with the transaction data object. Okay, first of all, is in which format these transactions are loaded into the smart contract, which is the data that is the data availability, which is on chain. Okay, and we can see here that we use kind of, I would say, special transaction encoding. Okay, and basically the transaction encoding is the LP of the transaction, but it's not the transaction hash, but is the, I would say, a transaction message that is used afterwards in order to verify the signature. Okay, and concatenated with this data, we attach the signature, the signature. R, S, and B. Okay, so notice that the R, S, and B are not inside the LLP, but they are outside. And this is basically for convenience in order not to pass it later on inside the RAM. So we call this data, the transaction data, we hash it with a keycat, and we call it batch hash data. And with the batch hash data, we also hash the global exit route, which is basically the route that the bridge has. We also hash the timestamp and the message sender when this sequence batches call has been made in the smart contract. Okay. And also, we have at the very beginning this all accumulated with hash. Those all values are hashed together, and then I compute what we call the new accumulated input hash. Okay, you can see it here. There is like a, I would say, chain, a concatenation of the old accumulated input hash, new accumulated input hash, and the new accumulated input hash will be the new accumulated input hash will be the old accumulated input hash of the next batch. Okay, so here we create like a chain, okay, of hashes, and this is very useful in order to prove a sequence of batches, not just one batch. I just want to mention that the global exit route it's a very important parameter, which because basically here what we are doing is forwarding the route of the exit tree in layer 1 to layer 2, and we enforce that by circuit. Okay, and this is very important because it allows to perform the claims of the deposit that has been performed in layer. So, what are the inputs and what are the outputs of the batch? The inputs are basically what we saw in the previous slide. And also we add here the chain ID, which is hard-coded in the smart contract. And I wanted also to add here this kind of get transactions. Okay, and we will see afterwards inside the batch. But basically, this get transactions is add me all regarding the batch is add me all the transactions that you want, add me all the data that you want. But at the very end, inside the zkEVM, we will hash it as the smart contract does, and this hash needs to match. Okay, so it means that you are forced to put exactly the same data that has been hashed in the smart contract. Otherwise, the hash will not match. And the batch, when we process all the transactions, they have some output, which is basically if we change the state root because it has been some Ethereum transfer or call contract or whatever, it has a new state root. We have a new accumulated to hash. We have a new num batch and a new local exit route. Just very briefly to mention that the local exit route is basically the exit tree in layer 2, and we are forwarding this layer 2 exit route to the layer 1. Okay, so in case that anyone wants to transfer some asset from layer 2 to layer 1, of course in layer 2 we have the bridge, and the root of this bridge is forwarded to layer 1 through this new local. We will see how to do it. Okay, so let's process a batch. Let's start the processing of a batch. This is the initial, the main, I would say the main entry point to the ROM. Okay, and this is basically just loading some register into memory. In that case, into variables. Okay, we are just storing the old state root, the old accumulated hash, the old num batch, chain ID, global exit root, sequence address, timestamp, and batch to variable. I just want to mention that here we are storing the all exit root, for example, but here we use the dollar. It means that it uses the op intermediate value, and you can put here whatever you. Okay, you can put the value that you want here, but later on it will be checked. In that case, with the hash that the smart contract performed. So it needs to be exactly the same. So you are forced to use some value here, but you can put the value that you want. If you don't put exactly the same value, basically the proof will be invalid. Okay, before going on to the second step of processing a batch, I'm going to show a little bit example of how the hash works, basically. As I mentioned at the very beginning, we have three different instructions for hash, which is hash p, hash clear, and hash digest. Okay. So here, basically, this is an example of how to use it. Basically, what we need to do is to, when we want to start the hash, we need to have an ID for that hash, what we call the address. Okay. So imagine that the address is the registered IP, and it's 0. Okay, and I want to add some bytes. How many bytes do we want to add to the hash? This is determined by the registered D. The D determines how many bytes I want to add to the hash. And the registered hash post is basically the offset where I want to add those bytes. It's like the offset size, typical offset size here. Okay, so I'm adding bytes to the hash. Once those bytes are added and finalized, I will just close the batch with the instruction hashcalend, and also hashcalend takes this E register. So I need to assure that I'm closing the hash in this specific address. And if I want to retrieve the result of the hash, then I will perform the instruction of the hash calendar. And this is very useful because here we're going to see how to set a mapping in Solidity, but coded in the zkEVM. Very straightforward. How to set a mapping in Solidity. So first I'm going to explain that. So if you have a mapping in a smart contract in Solidity, if you want to add a value to this a key value, you first need to compute the key. And in Solidity, basically the key of a mapping is the key cat of the value that you want to add and the position of the mapping in the smart. In this case, imagine that the smart contract just only have one mapping at the very top of the smart contract. So the position will be 0, basically. And in order to compute the key, you need to add the value that you want to add in the positions. Okay, so what do we need to do now is to perform this hash. Okay, so first of all, I'm going to load the global exit root into the register A. We saw before that we are accessing a specific region of the memory. We're getting that value and we're putting the value into the register A. Okay. Here, since the hash that I'm going to do, the offset, I will start at 0. That's why we put here 0 to the register of the hash path. The two next lines are basically the identifier of the hash, what we call before this address. Okay, so we are generating like a new address for the hash that I'm going to do. That's it. So I load some variable that is in memory, I increase it by 1, and this will be the address that I'm going to use. And then I store the last ID user, because later on I will perform another hash. And then I will increase this variable by 1 again, and so on, in order to not overwrite any hash that I already did. okay, how many bytes are we going to insert to the hash? Because in that case, I'm going to insert 32 bytes. And here I'm doing the action of adding these bytes to the hash. So here, basically, I'm doing the hash k instruction. Add the address of E, which we can assume that it's 0, for example, and I'm going to add 32 bytes, and these 32 bytes are the op, the intermediate value. And what is the op? Register A. So here I'm going to add to the hash the global exit route, basically. Okay. Then, when you perform the hash k, notice that the offset that we set it here at 0 position, it is moved automatically all the bytes that you have added. So basically the offset is moved from 0 to 31. Okay, so now the hash post register has a value of 31, but you do not notice that because it is done automatically behind the curtain. Okay, I add 32 bytes, which is basically the global exit route. Now I need to add this 0 here in order to compute the storage position. Basically, and this 0 is this percentage global exit route storage position, which is basically a constant. We have a 5. I show it in the diagram that are basically system constant. Okay, and basically this constant is equal. If you put here 0, it will be exactly the same. So here we are adding 32 bytes to the hash. And so we have the global exit route, 32 bytes, and we have the 0, 32 bytes. And then we have the hash complete, so we need to close it, and we need to retrieve the value. So we're going to close it with the hash k length instruction, and we are going to retrieve it with the hash k digest. Notice, it's very important, notice that we are using always the same address, the E. Imagine that there is a 0 here. So address 0, 0, 0, 0. So we are performing this instruction on the hash in the address 0, not another hash. Okay, so here we are getting the value of the hash, and this value of the hash we are moving to the register C. So in C, now we have the storage position. What we need to do, what do we need to do now? What we need to do is to store the value of the mapping. And what is the value of the mapping? In that case, we put the timestamp in the value. Okay. And in order to store, we need to use the instruction of the sstore, which basically will navigate through the zkEVM state tree and add some value to a leaf. Okay. What do we need to configure in the registers in order to go specifically to that leaf in the state Merkle tree in order to store that value? What we need to save in the register previously is the storage position that we already have in the register C. We need to stretch the address, and the address will be loaded in the A register, and this is also a constant. So imagine here an Ethereum address of a smart contract, and also we will add the leaf type. Okay, in our case, the leaf type, when we write an storage in the Merkle tree, the leaf type is 3. But also, again, this is a constant in the system constant. So you can imagine here, for example, of 3. Okay, so basically, and which is the value that we want to store? It's the timestamp. So we are reading the time. We are reading here the timestamp from memory, and we load it into register B. So we have all the registers set in order to perform the sstore instruction. So we perform the sstore instruction, and then the state route is changed, and then we save it into the register of the state route. Okay. This is basically moving from layer 1 the exit route of the bridge to the layer 2. But this is a very important action in order to perform some claims in layer 2 when you have performed at the positive layer. Okay, so we load all the initial variables, we set, we forward the exit route from layer 1 to layer 2, and now we're going to interpret all the transactions. And in order to do so, we need to decode the transaction. And as I mentioned, the transactions in the call data are supposed to be LLP encoded. So what we're going to do is to take one for one each transaction and try to decode it. Why I say try? Because in the call data, it could be any data over there. It could be a transaction, or it could be garbage bytes. So when we are going to decode the transaction, we will realize if the transaction is well done. If it's not well done, basically we are not going to process that transaction. And in fact, if the call data are not all valid Ethereum transactions, are not, I would say, they are not valid encoding LLP transactions, we are basically going to not process any transaction, or we are going to discard the batch. And when I say discard the batch, it means finish the batch without processing any transaction. We're going to see a snippet of this decoding transactions, because I think it's a little bit interesting. I don't know if you are familiar with the LLP encoding. I don't know if you are familiar with the LLP encoding, but basically the very first byte of LLP says to you if there is just a single value, how the length is this single value, or if you have a list. Okay, so what we expect is a list. If we don't read that we have a list, then we're going to discard, okay, all these transaction data. Okay, so imagine that we have a list, and then we start reading. The first parameter will be the nonce, which is 64 bits maximum. So according to the other LLP specification, if you have a value between, I think it's 1 byte to 64, then you need to read first the length of the value. Okay, so here we expect to read this number, 2x1 or 2x89, which is the number of bytes that they are encoding the LLP. If there is more data over there, we will discard all data because it's not what we expect, and we finish the batch, but without processing transaction. So here we read the nonce, the gas price, the gas limit, the two, I mean, all the parameters of an Ethereum transaction. And at the very end, without being LLP encoded, we are reading the signature parameters, which is the R, the S, and the B. And then we finish the LLP passing. This is one of the models that needs to be audited. For example, and it's very important because here we decide if later on we are going to process the transaction or not. Okay, so once all the transaction data is processed, what we are going to do, once all the transaction data is decoded, what we're going to do is to process these transactions. And processing the transaction does not mean only to call the smart contracts and go code by your code and interpreting these codes, but it also adds some, we need to perform some checks at the very beginning, which is basically the intrinsic check that you can find in the yellow paper, because as I mentioned at the very beginning, we are processing not just only the EVM, but we are processing non-compatible code to the EVM. Okay, so here we can expect some sequencer to add data regarding a transaction that with different nodes that the sender has in comparison to the one in the state tree. So we need to check that indeed this transaction has exactly the same nodes. Otherwise, this transaction could not be processed, so we skip it and we go to the next transaction. So here at the very beginning, we are doing these intrinsic checks. We are verifying the signature. We are verifying that the sender has not any deployed smart contract. There is a specific API, a specific check that we need to do. We are verifying, of course, that the chain ID is exactly the same that the one that we have in the smart contract. That's why the chain ID is an input of the batch and it comes from the smart contract. We are going to verify the nodes. We are going to verify that the sender has enough funds in order to pay the transaction. Those are, I would say that basically those are the intrinsic checks. Once all the requirements are met, what we are going to do is to execute. We are going to process the transaction. Okay, so what I'm going to do is to go to the piece of code in which we are interpreting the EVM, the smart contract bytecode, I would say. Okay, so basically, once all the intrinsic checks are met, we are going to call the contract. Okay, here, as you may know, in Ethereum there are different transaction types. There is the deployment transaction type, the Ethereum transfer, or a call contract. So in that case, I assume that we have a call contract because I think it's the more interesting code to see. And when we perform a call to the smart contract first, we are going to move the balance. And later on, here it's an important piece. We need to be assured that the bytecode that we are going to interpret is indeed the bytecode of the smart contract that we want. Okay? So in order to do that, what are we going to do? What we're going to do is we're going to create a new identifier for the hash, okay, which is basically here. And we're going to fill this hash, okay? And here, as we saw when we set the global exit route from layer 1 to layer 2 in the zkEVM, we are putting the offset in 0, and here I'm going to add byte by byte of the smart contract. Okay, so here I'm basically adding 1 by byte. So here I put the offset to 0, I put the size to 1, which is the D, and here I perform the hash key, which is basically adding 1 byte to the hash. And what is the byte that I'm adding? And I mentioned previously, if we found this dollar with this kind of brackets, you can put whatever you want here. You can put whatever you want. You can put any byte that you want. Okay, so we are adding just bytes to a possible hash, one after the other. And when we finish, we close the batch, we retrieve the result of the batch, and what we're going to check, and here this step is very important, what we're going to check is that the result of this hash matches exactly the byte contract hash that we have in the state method. So here I'm assuring that the bytecode that we are going to interpret now is the bytecode that this smart contract is supposed to have. Okay. So here I'm going to read now and interpret the bytecode. Here with bytecode, and basically here we are just from the. You remember that I said that we are just adding byte by byte the smart contract bytecode into this hash. So from this exactly bytecode that we add here, we are reading all the bytecodes that we are going to interpret using this functionality. So the hash key is not just for only writing into the hash, but also for retrieving from the hash. So here we're retrieving byte by byte, and basically we have a table with all the opcodes, and this table will relate to the opcode that you want to interpret. Okay, so imagine that we have a smart contract that interprets one opcode, and this opcode is the addition add opcode. Okay, so we're going to check now the implementation of the add opcode. At the very beginning of the add, we're going to perform some checks. One of them is regarding the zk gas, and in this case is the zk counters, and is basically we run out of counters. Okay. Afterwards, we'll perform exactly the same checks as the EVM does. So we need to check that, for example, in this addition of add, in this opcode, we need to read two values from the stack. So we need to be assured that indeed there are two values in the stack. Otherwise, we will jump to a special routine, which is a stack underflow, which handles that error. Also, we need to check that we have enough gas in order to perform this opcode. And later on, what we're going to do is to read two values from the stack. And this is pretty much the same that we did in the example that I showed at the very beginning, at the end of the zkEVM section. Okay, so we are reading the A, we are reading the B, we are adding using the binary machine, and we store the bytecode in the stack. And what we do when we finish, let's interpret the next bytecode in the smart contract platform. Okay, I would say that this is a very straightforward opcode, which is the addition. But for example, if we go to the multiplication, it will be also a little bit straightforward, but we will see that we use here the more the arithmetic state machine as well. So in the multiplication, as you may know from EVM, we are also reading two values from a stack. Okay, and we need to multiply them. In order to multiply them, we're going to use a utility that we built, which is called most added. I will show you, and basically, let me find it. Okay, and basically, what it does is it performs the multiplication. Okay, but it performs the multiplication using. I mean, you can put whatever you want here using this $, or this $. Okay, so we are putting here the result of the multiplication. We could say, and later on, using the arith state machine, we are checking that indeed the value, the result of the multiplication is indeed that value that you perform. So is this thing that you add whatever you want, and later on we check it. Okay, so it happens the same in this state machine, in the mul opcode. Okay, so in order to finish, once all the transactions has been processed, in order to finish the batch, what we need to do, we need to basically compute exactly the same thing that the smart contract did. As you remember in previous slides, I showed you what the smart contract hash does. It does basically a keycap of the all the accumulated input hash, all the transactions hash it all together, which is the batch hash data, the global exit route, the timestamp, and the message sender. So in the ROM, we need to perform exactly the same in order to assure that we use this data. Basically here we are just while we did the IRP decoding, we add all of this data into the hash. So here we are closing that hash. So we are computing the batch hash data. And here basically, as you see, the offset is set to 0. We are adding 32 bytes, and we are adding the alt accumulated input hash. Perfect. Here we're in 32 bytes, and what we are adding, that's data. Here we're in the global execute, the timestamp, the sequence address, and here we are closing the hash, and here we are retrieving the result of the hash. The hash must be exactly the same as the one that we compute in the smart contract. So here is the new accumulative hash. Okay, and just to finish, remember that when Jordi and Jose explained the state machines, they explained that the state machines need to be cyclic. So in order to finalize the execution, we need to be sure that the registers that were set at the very beginning, they need to be exactly the same at the very end. Okay, so here I would say we're just like finishing this execution. Okay, so here you have links of resources that you can check. As I mentioned, all the code is open source and it's available on GitHub. I also mentioned very briefly at the very beginning the difference between the state tree of the EVM of the zkEVM. If you want to look further of the specification of how to build, how we build the key of the Merkle tree and so on, I give a talk. It's still last summer, and you have the slides here if you want to check it. And okay, that will be all. Thank you very much. I hope you enjoyed this session. Thank you.
If nobody has any question, I would like to, well, just to summarize. Okay, what we have seen today is just a language that's running on top of the zk processor. Okay, where we implement all the zkEVM. This language is an assembly language. It's quite specific. It has actually it's a language that does not compute things. What it does is, well, it moves registers in a very low level, and it ensures things. So when it's doing an operation, actually it's checking that the operation is valid. It's checking things. Okay. The language is a little bit different of the typical assembly languages, especially this beginning. This is because these registers, how you do the moves between the registers and how you load, is the most important thing is this OP register, this intermediary register. This is something that in each instruction you load. Okay, so you load something to this OP, and then you store what this OP to some of the other registers. Okay. The other important thing is the hashing. The hashing is, well, the idea is quite a little bit the same. The idea is that you have a table of hashes. It's like another memory where you have all the hashes, and then you are just checking that a segment of this table, so that a portion of this table matches with the other table. So, for example, with this hash, with this string that has a string that can be variable size, with a given hash, you can check that at a specific point, as many bytes matches to this value. So you can check with the batches. So this is the way we have to compute hashes inside the program. The other instructions are quite trivial, arithmetic, operations, memory reads, memory writes, storage reads, storage writes, have the most the typical, and source normal operations. And with this, we built all the zkEVM. Here, the starting and the ending. It's at the start, at the beginning, you have all the what is the public inputs of the circuit. Carlos said that they are already stored in the beginning. Actually, this is checked in the pill. In the pill, we are checking that the public inputs are set at these registers at the beginning, and the public outputs are set at the end of the register. And from here, we just compute, just don't know what exactly the same that Geth does or that any Ethereum client does, just processing these transactions. We are building this hash, and this hash is what's public input, what's the public output, and then we just match that this hash is correct. Okay, so yeah, just maybe going through the code is probably the easiest way. Here, you don't have to deal with well, just a code that's very explicit to that. But yeah, this is a little bit how we are building the zkEVM. It's a little bit, I would say that's a little bit different of how the scroll people does. But at the end, we are doing more or less the same. So at the end is the idea is yeah, at the end we are computing somehow the same in a different way, but it's the end we're just emulating the zkEVM. Okay, so that's very much the summary. So